Hey peeps. So what we have here are two expressions that show the relationship between the period of a gravity pendulum and the period of a spring pendulum. As we noted from our labs, the period of the gravity pendulum depends on the length of the pendulum in meters and the acceleration due to gravity, g, in meters per second squared. So that happens to be a constant because of where we are, but if we were to go somewhere else, like the moon, if we could do that, then the period would be affected that way. Spring pendulums have a similar look to it, similar format. The period is 2 pi times the square root of m over k. M is the mass in kilograms of whatever object is attached to the spring, and k is the spring constant, the stiffness of the spring, in newtons per meter. Now, this is all well and great in terms of the physical variables and describing the length of the period or the amount of time that the period is, but we can go one step further and look at the actual motion of the pendulum in terms of what is called simple harmonic motion. And so to do that, I'm going to bring up a couple of simulations that can also show us the graphical relationship between the position, velocity, and acceleration of the pendulums in time. Hey there peeps. So here I've brought up a freely available Java applet that will simulate the motion of the pendulum and also graph it in a way where we can see in this case, the elongation or the displacement from its maximum angle over here. And we can see it move through time. So I'll start this up so we can take a look what's going on. Okay, so we see the pendulum going back and forth. The oscillation period is 4.49 seconds. That comes from, in green over here in this field, the length is 5 meters. And so we can calculate that oscillation period using the equation that we saw before, 2 pi times the square root of L over G. We get 4.49 seconds. And so what we see here is that if we track this through time, then the pattern is sinusoidal. So it creates a sine wave. And actually, if I reset, we see that it's actually a cosine wave. The reason is we're going to start it off at its maximum position over here. Then it goes, and I'll pause it, to the position where it's at its equilibrium, okay, the length of the string over here. But then it continues through and goes to its negative most position like this, all right? And it keeps doing this over and over periodically. So one of these full sine waves is equivalent to one period of the oscillation. So I'm going to reset this for a moment, and we can take a quick look at velocity. And velocity has the same kind of relationship, except we'll note that it actually is a sine wave, a negative sine wave. For those that are taking calculus, that's because if we look over here, position, the derivative of position is, well, velocity. So the derivative of the cosine is negative sine. The amplitude we'll deal with later, being that right now it's just a little more than 1. Amplitude here is expressed in degrees, 10 degrees. We can also change that as well. And then the derivative of velocity is acceleration. Okay, so what we have here is a negative cosine. The derivative of sine is negative cosine. And so those who've done a little bit of calculus can all put it together, but all of us can see that there's a little bit of a shift here when we look at displacement, velocity, and acceleration like this. All right. Now, if I were to change something really quick, and I can give you the link for playing around with this. So let's make the length 2 meters. All right. And I'll reset with 2 meters. We can see that these are bunched up more. It's happening more frequently. Why? Because the oscillation period goes down, and what we see is that these guys are bunched together a little more. If I elongate to 10 meters, the period is longer. This doesn't occur as frequently, okay? And what we're going to look at next is the spring pendulum, which has a similar kind of relationship through time. We can track it through time and see that it moves in this sinusoidal pattern, which is characteristic of something known as simple harmonic motion. So this simulation, similar to before, has a pendulum, but this is a spring pendulum. And so what we can automatically see in this plot over here is that there's the time axis once again, and we have a displacement, which is known as the amplitude. In this case, it's not swinging back and forth, but it is bobbing and jumping up and down. So it's got that little boogie. So for a spring, we have different parameters. The spring constant, 20 newtons per meter. Mass is 5 kilograms. The acceleration, well, we can change that if you like, if you want to play with that and see how it affects the situation. And then the amplitude, okay? Now, similar to before, we start off at its maximum position, in this case, the highest position, and it will move, if I start this, to its lowest position, like that. And so here on the graph, as it's tracking motion through time, we can see that it began at the highest point, positive, and goes to the highest point, negative, which is the low point here. And we have the same kind of relationships as we did for the gravity pendulum with velocity, acceleration, and we can also look at force and energy. So the real crux of this, though, is that we still have this sinusoidal pattern. So I will start it up here. And what we have is the pendulum bobbing up and down. This is like a bobblehead, and we can see it has a representation in time of a sinusoidal shape. Okay, so that is indicative of the simple harmonic motion. In this case here, the period is 3.14 seconds. If I were to change this to, say, make a stiffer spring, we'll see that the frequency here changes. Okay, the oscillation period is shorter, 2.22 seconds. So it's going to bob up and down more frequently. More of them are happening in any given amount of time. And if I were to change the mass, make it heavier, it would start to slow down a bit. Okay, so we can play with these variables here. But the key is that the spring pendulum, just like the gravity pendulum, exhibits this thing called simple harmonic motion, which is a sinusoidal relationship through time. We're going to look at some of the basic representations mathematically before relating it to everyone's favorite topic in pre-calculus. If you haven't gotten there, you will at some point. The unit circle, or something known as the reference circle. So I wanted to get just a little bit mathy on describing what this simple harmonic motion stuff really is. So x is the displacement, let's say, of the gravity pendulum or the spring pendulum. A is known as the amplitude. So it's basically how big is that swing. And then what we saw is that the pattern with respect to time is sinusoidal in nature. So what that means is for the displacement, if we start off at one of the maximums, it looks like a cosine function. Inside the cosine is 2 pi divided by t, t being the period in seconds. So what that means is as t is running, so as this thing is swinging and t starts from 0 and moves forward, and is a multiple of the period t. So when little t equals big T, the oscillation repeats because this is equal to 1. And at least in terms of radians, if you've learned in pre-calc or whatnot, that the cosine of 2 pi is going to be 1. And so we have the A as our amplitude over here. So this thing describes how it moves in position. Here we take a look at the velocity, and as I described before, for those who have taken calculus, you're doing, if you've done derivatives of trigonometric functions, you've got the sine function here. So its negative sine is the derivative of cosine. That's what velocity really is. And what we have over here is, not going to worry about too much about the technical aspects over here, but we see that here's the amplitude, but it's the same kind of relationship here, a sinusoidal relationship. Again, as t, big T approaches little t here, it's the sine of 2 pi, which is 0. So in that case, velocity is 0. But velocity maximum occurs when the sine is pi. So it's t is, big T is 1/2. All right. So in that case, or it's half the period. What that means is that we have a maximum velocity, though, of 2 pi divided by t, the period, times whatever the amplitude is. Okay, so this thing, as it moves back and forth, it of course has some velocity, and its maximum velocity is going to be right in the middle of the spring, or that equilibrium point, or in the case of the gravity pendulum, at the very bottom. And this one also describes acceleration. We take it a little bit further. So that's just wanted you to take a look at what the mathematical description is. Might be helpful, and that's something you can relate to your math classes so far. We're going to take one final look. It's another simulation at how we can visualize both the circular motion and how that relates to the simple harmonic motion. All right, so here we are. We've got circular motion here, and what I'm going to do for you is use this simulation to show you that simple harmonic motion is related to the circular motion, and thus the unit reference circle. So let's start this animation. Okay, so what we see is that the red vector indicates velocity, which continues to change direction. This is v tangential of the circle, and so it goes round and round at a constant omega. So the angular velocity is constant. There's no angular acceleration. And the blue line is just the x component. It's just the x projection. So what we see here is that it's just related to the trig of this right triangle. Let's pause it for a moment. So for example, over here, this position here relative to this hypotenuse is going to be based on the, well, if you look at this angle over here, it's the sine, or if this angle over here, it's the cosine. At any rate, what we see is that this dot over here is going to go back and forth just along the x-axis, just like a pendulum might do the same thing. So if we imagine a swinging pendulum going back and forth, that blue dot, it actually will track in the same kind of motion that a gravity pendulum would, back and forth. I could do the same thing on the y-axis over here in kind of orange. This is like a spring pendulum. So this is going up and down and up and down, and it's doing so exactly like a spring pendulum would. So this type of motion that has the sinusoidal relationship through time is all based on motion around a circle going at a constant omega. So a lot of things that you guys have learned are actually quite interrelated when you put them all into motion. So it's all pretty technical stuff, but I think it's something that you guys can certainly handle if you think about it. And it's visual here, which is kind of nice. We'll go back to the blue. Here we go. The side to side, like the gravity pendulum. And so, what we see is that we can take what's called a projection. So I'll actually show this by the use of shadows. So we can actually totally see something that's moving in a circle will, on one two-dimensional axis here, on a two-dimensional projection, we can see it as simple harmonic motion. So that's what it is. So thanks for hanging out on this extra credit video. And that's what it is. Morad out.